Okay, we're going to continue on here, chapter 14. So we've been wrapping up here the last bit of our organic groups. So last time we focused in on our carboxylic acids and our esters. And again, a carboxylic acid has that functional group of carbon-oxygen double bond with the OH group attached to it. Our esters is the carbon-oxygen double bond to the oxygen and attached really to a carbon. It doesn't have the H there. In terms of how we name our carboxylic acids, as we talked about, really this group will always be at the end because of the hydrogen that's attached there. So you kind of put the oic acid on it. So again, if you had something like this, perhaps, that is 2 carbons, which is based off of ethane. And again, this is what is known as ethanoic acid. Our esters, on the other hand, are named some way, but I think we go O8 at the end of it. And there is like an alkyl sort of group name that comes from the alcohol. So remember that really our esters comes from an esterification reaction, as we talked about. And that basically is when we throw together our carboxylic acid and an alcohol. We basically make water. And water goes out. And then that is how we put together our ester group here. So remember that you could really split the ester bond kind of always between the carbon and the single bonded oxygen. And heading towards the single bonded oxygen is always the alcohol part. And that alcohol part is basically the alkyl name. So again, if you had like 1 carbon, that would be like a methyl. The going towards the carbon-oxygen double bond the other way is really our carboxylic acid part of our ester. And that is really the number of carbons, and then kind of drop the E and put O8 at the end of it. So if we had some type of ester, I want to just build out this guy right here. Why not, since we have him? We'll do something like that. So again, if we were to break this ester right here going this way, which is our alcohol, we have only 1 carbon, so that would be methyl. Coming the other way, which is our carboxylic acid part, is 2 carbons, which then would be ethanoate. Yeah. And this reaction on the bottom, which is how we produce a ester through the esterification reaction. We talked about as well how we get to a carboxylic acid. Again, it really all could originate from a primary alcohol that gets oxidized to an aldehyde. And if that guy gets further oxidized one more time to our carboxylic acid. So that's sort of the pathway as to how we get to our carboxylic acid. Remember, as we talked about the carboxylic acids, because it has really those kind of 2 polar groups on it, here where the carbon's more positive, oxygen's more negative, and here obviously the OH as well. It is typically very soluble in water. Again, less than like 4-ish or so carbons. Much like everything else, solubility does decrease as we build out the carbons, as we talked about. It also will have a very high boiling point because it's able to actually hydrogen bond with itself. At those 2 points, it could make a dimer together as the 2 of them come together and really hydrogen bond strongly. So as we talked about, carboxylic acids are one of the few sort of organic groups, if you will, that could be in an alcohol in terms of boiling points and melting points. But alcohols usually could beat almost everybody else. But carboxylic acid, because it has those 2 groups, are able to do so. Let's see here. Any questions on any of that stuff there we talked about last time? All right. So I think where we laid up was hydrolysis of esters, and hydrolysis means water is involved. So if you think about sort of how esters are formed, as we talked about, they are formed again from basically removing water. So really, this reaction where we kind of do the hydrolysis will kind of break the ester back apart. Perhaps depending on the case, it could break it back apart into the carboxylic acid and the alcohol. And in some cases, it may not get the completed sort of carboxylic acid back, but it's sort of the reverse-ish reaction of kind of putting it together is hydrolysis by basically kind of putting the water back into play. So there's two types of hydrolysis. One's an acid hydrolysis and one's a base hydrolysis. And you really do get sort of two different outcomes depending if it's done in acidic conditions or if it's done in basic conditions. So we're first going to talk about what happens when we do it in acidic conditions. And this is how you kind of know it's acidic conditions. That H plus basically tells you it's acidic conditions. So if you see an H plus written over the arrow, that indicates that it is acidic conditions. Heat also sometimes represented with just a little triangle. Sometimes people will use that to represent heat. So what happens when we do acid hydrolysis is the water molecule basically will help us rebuild back both parts of the ester. So do acid hydrolysis, you will get back your carboxylic acid sort of completed, and you'll also get your alcohol back. So if we think about just looking at sort of our ester group here, like we have down there at the bottom. And if we add water, again, we can think of water in this case as H and OH. And just like how we put the ester together, we will obviously break it apart at the exact same spot. So the sort of breaking off point is going to be exactly where we put it together. And the nice thing about this is if you understand that it is the acid hydrolysis here, it's sometimes good to know where you should end up. And you should end up in this case with basically a carboxylic acid and an alcohol. So with that being said, nothing disappears here in this process. We're just going to kind of add things in. So what we would want to do if we were going to draw this is simply just kind of draw the parts of what we would get if we broke it apart there. And that is basically just the two parts here of our ester. So what we know is we should get a carboxylic acid back and we should get an alcohol back. And really what's left is we're going to use water basically to do that. So if we think about our alcohol in this particular case, it is only short a hydrogen, right? So our hydrogen is going to end up over there. And now we have completed back our alcohol. To complete back our carboxylic acid for the guy there on the left, we pretty much need an OH, which is very convenient since there is an OH left there after water kind of gives away its H. And that OH is going to come back here and we're going to get our carboxylic acid back. So you could kind of think of the acid hydrolysis of an ester as kind of the reverse of this esterification reaction, where we take water out and kind of push everybody together. And when we go the opposite way with the water and the acid hydrolysis, we're going to break it apart exactly where we push it together and then really rebuild the two sort of organic guys that are there. Absolutely nothing else changes in terms of the other parts there. We're just going to kind of rebuild our carboxylic acid and our alcohol. Questions on that though? So let's take a look at this though. Actually, let's take a look at one here. Let's just do one here. So let's say we had this ester here. And we add some water under acidic conditions. I'll go this way. Some heat. There we go. All right, draw what you would get in this case here. Okay, let's take a look. So we see water, we see an ester, we see acid, basically, conditions. So all we have to worry about is, I know it should break apart right there. And again, you could just start by redrawing the parts there. So once again, I'm not going to change anything other than just redrawing what was there. Obviously, I'm going to kind of separate it up there. And we'll go this way. And again, here we should get back to completed alcohol and our carboxylic acid. And we're going to really kind of build that out using our water. So again, our H is going to come down here. And our OH is going to come over here in this case. Any questions on that one there? So again, this one is not too bad. Just break it apart, kind of put back the parts to get back to your alcohol and your carboxylic acid. Yeah. Oh, what would these be? I have no idea. Let me count. 1, 2, 3, 4, 5. So that would be pentanoic acid. And this would be 1, 2 ethanol, yeah, which is your carboxylic acid in your alcohol. Yeah. Other questions? Okay. So this is the acid hydrolysis of an ester. Again, you do get back, like I said, both of those things, the carboxylic acid and the alcohol. Let's talk about the base hydrolysis, which is sometimes referred to as saponification. And in the base hydrolysis, we use a strong base, like something like sodium hydroxide. And in this particular case, we actually do not get back both parts of the ester. We actually do get back the alcohol part, but we end up with a salt of the carboxylic acid. And that's because we're using a base here. So we're kind of missing out on the hydrogen from the water, which is H2O. So in this case, we actually only have one hydrogen to give and an oxygen to give. So in this particular case, we're going to break this guy apart in the exact same location as the other one. Here is we basically have like NaOH, and this is obviously a base here, right? So that's a base. So that's why it's the base hydrolysis. So when we do break this apart, you really can't approach it the same way. You can just draw the parts just like we did previously. The difference here is the only thing that you're going to really be able to sort of complete back is the alcohol. So it's going to kind of steal the H from there. We'll just pretend that's where it gets it from. And if you kind of look at it at that point, we're kind of left with just an oxygen and a sodium at this point. And this oxygen actually will end up here. It will actually have a negative charge, which is why it's referred to as a salt. And the sodium actually has a positive charge, and they're really ionically sort of together in that case. So here we get the alcohol back in the base part, but we get a carboxylic acid salt is referred to. And that's basically just like the carboxylic acid, except it's missing a hydrogen, basically. It'll have a negative charge on the oxygen because it's missing that hydrogen. This is what's referred to as saponification, because this is basically how you make soap. So soap is pretty much made through this process using some type of fatty acid, which has a super long carbon chain. And at the end, when you do this reaction, you end up with basically a really long molecule of carbons and hydrogens and this sort of salt part at the end. And what makes something like this, which is soap, sort of work, hence the saponification part, is it has two parts. It has a polar head, which is where that charge is. And then all these carbons pretty much and hydrogens, this is the non-polar part that's sometimes referred to as the non-polar tail of soap. And that's basically how come soap works really well, because dirt is pretty much non-polar. So the non-polar part of soap, which is all those carbons and hydrogens, pretty much trap the dirt. I'm just going to do my wiggly lines as my carbons, pretend they're carbons. And what that will do is actually leave the polar part of soap on the outside after it kind of traps all that dirt in the inside. And that's really good because typically after you soap up, you do what? You wash it off with water, which is polar, right? And the water is attracted to the polar side of soap, which is now kind of positioned on the outside. So that will allow soap to mix with water, and in the inside, which is sometimes referred to as a micelle, all your dirt and grime is pretty much trapped in there. So as you wash off the soap takes the dirt with it and you're clean. Good to know how soap works, I suppose. Yeah. So any questions on that there? I think we also discussed it in the lipid chapter. I think perhaps we might talk about it there as well. All right, so let's try one more here. Just make sure we can do both the acid and the base hydrolysis of methyl acetate, which is more common name is methyl ethanoate. Actually, it's IUPAC name, it's methyl ethanoate. All right, so draw what you get with water hydrolysis, acid hydrolysis, and base hydrolysis on the bottom there. All right, let's take a look. So we'll start with drawing the methyl ethanoate, which is our ester. Remember that when we're drawing an ester, it's a good idea actually just to start with sort of the ester connection. The methyl is the alcohol part, which goes to the single bonded oxygen. The ethane part is the carboxylic acid part, which goes to the carbon oxygen double bond. The important part is to remember you already have a carbon there, so ethane is 2, so you just need one more carbon. You don't want to add an extra carbon since you already put one there. Now we're ready to roll. That we got that all squared away. We're going to do a little water action with it here. Once again, we're going to break right there where we put it together. And when we do that, we will get CH3 C double bond O plus OCH3. And once again, since this is the acid hydrolysis, we know we should get back basically both things that we started with. So again, this guy is short just a hydrogen to get back to the alcohol. And this guy is short the OH, which obviously both come from our water in this case. Yeah. Any questions on that one there? Now doing the same thing here in the base aspect here. We're going to actually add KOH here, so it is going to be a little bit different. We once again are going to break it apart right there. I'm just going to draw it up here. Now remember, in this case, when we do the base, the only thing that we really can sort of put back together completely is the alcohol. So we can definitely put the H on there, and then frankly, you could cross it out, and you're left with an oxygen and a potassium. It's important to remember that the connection here for the carboxylic acid salt really here is the carbon to the oxygen, again, not to the potassium. So or the sodium, if that be sodium. That technically really has a negative charge, which is why this is a salt of a carboxylic acid. And you can put the K plus there as well, again, just to really balance out this charge there. And again, we get our alcohol here. Any questions on either of those? No. All right, there it is. That's good. I'm glad they agree. All right. Then let's move into the final two groups of the season here, which is amines. Amines are nitrogen-containing groups. They basically have the functional group of like NH2, that nitrogen sort of containing group. They really are derivatives of ammonia. Yeah, so they are basically derivatives of ammonia. They share a lot of commonality there, which with ammonia. They also have some non-bonding electrons there on the nitrogen in most cases. So amines which are derived from them basically have the nitrogen, and depending on the type of amine, it may have some groups attached. It may also have an aromatic. Remember that this guy here we saw earlier when we talked about benzene, that has an historical name of aniline, right? And that's that nitrogen containing group that has the benzene group on it. In this case, we have our nitrogen, and again, replacing some of those hydrogens that would be there are some carbon groups. So typically the basic primary type of amine will have 2 hydrogens. And then for every kind of carbon group you put on to the nitrogen, you lose a hydrogen. So you kind of take a hydrogen off, put a carbon group on there. So you can see this guy has 2 sort of carbon groups attached to it, so it lost both hydrogens. This guy here has only really 1 carbon group attached to it, so it still has its 1 hydrogen still there. So depending on the number of carbon groups you sort of attach to that nitrogen, you do have to sort of sacrifice a hydrogen when you do so. Now, we can classify amines just like we classify carbons and alcohols as primary, secondary, tertiary. The difference here is instead of looking at the carbon that's like attached, we actually look at the nitrogen and how many carbon groups are directly attached to the nitrogen. So this obviously here has one carbon group attached directly to the nitrogen, makes it a primary amine. This nitrogen has 1 and 2 carbon groups attached to it, which is a secondary. And then obviously here at the end, our nitrogen here has 1, 2, and 3 carbon groups attached, which makes it a tertiary amine. So as we sort of attach more groups to the nitrogen, it goes from primary, secondary to tertiary. And again, here it's a little bit different than how we classify other things that we've done. It's actually, we are looking directly at the nitrogen here and how many carbons are directly attached to nitrogen as the classification point. Unlike an alcohol where we look at the carbon that's attached to the OH and how many carbons are attached to that. So it's an important difference in terms of how you classify them. So here's a primary amine, which is methylamine. This is dimethylamine, which is a secondary, and this is trimethylamine. These are the common names of naming amines where you basically kind of like what we do with ethers. You look at the groups that are attached to the nitrogen. So that's 2 methyl groups, which gives it a dimethyl. Attached to the nitrogen, 1 methyl group, which is a methyl. And you basically just put amine at the end of it. And here that has 1, 2, 3 methyl groups attached, which is how it gets to trimethyl. And again, you just kind of put the amine at the end of it. So that is how we'll go about naming these guys, which is more of a common name sort of approach. And again, it's very similar to our ether sort of way. We just basically go to the nitrogen, and anything that's not a hydrogen attached to nitrogen, we name the group. That is ethylamine. And again, here we have dimethylamine. And this guy here, that is dimethyl. And we also have a ethyl group attached here. And again, alphabetical order on the group. So ethyl, dimethyl, once again, ignoring the prefix. So M comes after E in this case, when we ignore the prefix. Now, the more IUPAC way of naming it, the more official way is, especially with secondary and tertiary amines, is you may sometimes see this sort of written. For example, we'll take a look at this guy here just to kind of show you here. Now, the sort of IUPAC way of naming is you take the longest carbon chain that's attached to the nitrogen. In this case, they're both the same. And you call it methane, you drop the E, and you put amine at the end. Now, the group here is actually attached to a nitrogen and not a carbon. So normally when groups are attached to carbons, we give numbers, but here it's actually attached to the nitrogen. So sometimes they will use N-methyl, methanamine. The N means it's attached directly to the nitrogen. So like how we usually go like 2-methyl or something like that, it's attached to the second carbon. You'll sometimes see that. If we look at like this guy down here, which is a tertiary amine, the longest carbon chain is actually 2 carbons that are attached to the nitrogen, and that would be based off of ethane. And again, you kind of drop the E and put amine at the end of it. Now, these groups would be dimethyl, but they are each attached to the nitrogen. So just like when we have groups, the same groups or whatever attached to different carbons, we give the number, right, for each of them. Here, they'll sometimes write N, N, dimethyl ethanamine. Both of those N's mean that the methyl groups are attached to the nitrogen. So if you happen to come across that sort of naming, that's really the IUPAC way of naming, the official way of naming it. And sometimes people get freaked out, like, what does the N mean? It basically just gives you the location of where that group's attached to the nitrogen, rather than it being attached, obviously, to a carbon, where we usually use numbers. So we typically use numbers for carbons, and if it's attached to a nitrogen, sometimes people will use N. For us in here, as I mentioned before, we'll just roll with the more common sort of naming here, where we kind of do the groups and just put amine at the end. But just in case you come across it, that's what the ends sort of represent if you do happen to see that. Any questions on that there? All right, so why don't you give the name for each of these, common name, and also classification, primary, secondary, or... Okay, let's take a look at the classifications here. So remember, when we're classifying amines, we are looking at the nitrogen and how many carbons are directly attached to it. So in this case, that should be a primary. Here we would be looking at the nitrogen, and again, how many carbons are directly attached to it. And in this case, it is a tertiary in this case. Any questions on that there? Now, again, we're going to kind of take like our ether approach. We're just going to kind of maybe box the nitrogen. And again, anything that is a carbon group, not a hydrogen, but anything that's a carbon group is what we're looking for. So here we have a 3 carbon group. So that's a propyl, I hope. And then we're just going to put amine at the end of it. Looking at the nitrogen down here, we have a methyl group there. We have another methyl group there. So that's like a dimethyl action happening. We also have a 2 carbon group, which would be an ethyl, which actually, again, would come first alphabetical because we're looking at the M versus the E here. We're not looking at the di part of it, the prefix. And then we just should put an amine at the end of that now. Any questions on that name there? Now, let's say we wanted to, yeah.
Is anything to the left of the nitrogen?
It's it doesn't necessarily have to be to the left. It could be to the left, right, up, or down, to be honest with you. But it's really anything that is directly, any carbon group that is directly attached to the nitrogen. That's what you want to look for. There is actually no longest one here because we're doing more of a common name with this. So we're just going to put amine at the end. And then we're going to name everybody else that's a carbon group as a group, like an alkyl group. So like a methyl, an ethyl, propyl type of group. Yeah, so that would be dimethyl ethanamine would be the IUPAC way of naming it. So this is the common name. So for us, we're going to go common, but you would be correct actually in terms of if you put NN, dimethyl ethanamine, then you would be correct in terms of the IUPAC name. But for us, we're just going to go kind of common name, which is basically group, alphabetical order, and then just put amine at the end of it. Other questions? All right, so some of these aromatic amines, again, aniline, as we've talked about before, is that benzene ring. Again, it's got to have double bonds in there for it to be benzene. And here is our aniline here, and this will be carbon number 1, 2, 3, and 4 going that way to our bromine. And here, this would be N-methyl aniline. So here's where that N comes in, as we were just talking about. So basically, this entire part here is our aniline part. And I'll extend it here, make it bigger. That line there is a methyl group at the end of it. But again, that methyl group is not attached to a carbon. It's attached directly to the nitrogen. So that is where the N-methyl comes from. Basically says that the methyl group's attached to the nitrogen, and the big part of it is still aniline. So again, if you see that N, that is what that represents. Any questions on that? Okay. All right, so write the common name for each of these, and why don't you also draw ethyl, butyl, amine. I know it should go the other way around. I know I'll learn the alphabet soon. Hang on a second. Do the right thing here. Hang on. All right. I guess B comes before E, right? So butyl, ethyl, amine. All right, let's take a look. So once again, we're going to focus in here on the nitrogen. That looks like a 2-carbon group, which is an ethyl. That also looks like a 2-carbon group, which is an ethyl, and that is a 1-carbon group, which is a methyl. So going common name here, we have 2 ethyls, so that's going to be diethyl methyl amine. Once again, ignoring, we're just going to compare these for alphabetical purposes. Any questions on that one there? This big guy right there, that's going to be aniline. And that is going to be an ethyl group that is not attached to a carbon, but it is attached to a nitrogen. So that's going to be an N in place of a number because it's attached to nitrogen, ethyl, and aniline. Any questions on that one there? All right, so what's left is to draw whatever I did there. So that is, in this case, it's an amine. So frankly, I'm just going to start with a nitrogen. And then I'm just going to kind of add my group. So butyl is 4, I think. 1, 2, 3, and 4. And ethyl is 2. Going to fill in some hydrogens here. Now I also need to fill in a hydrogen on the nitrogen as well. Yeah, I could go up or down. It doesn't really matter in this case. Yeah. Again, we need it. Otherwise, really, nitrogen there will be short a bond. So this is a secondary amine, so it should have 1 hydrogen left over. The tertiary amine, like we have up on the first one, doesn't have any hydrogens left over. And really, our aniline there is a secondary amine, yeah, as it has basically 2 carbon kind of things attached to it. Any questions on amines, how to draw them, how to name them? Okay. All right, so if we were going to do some type of line structure, obviously like normal, we would do our kind of zigzag guys for our carbons. And obviously we would need to write the nitrogen in the middle there, or wherever it needs to be for it to happen. This is a primary amine, again, attached to 1 carbon. This is a secondary amine, 2 carbons right there attached. And this would be a tertiary amine, which has 3 carbons attached at that point in sort of line structure. So again, you can still classify it the same way, and you would name it obviously like we were doing there in terms of common names for each of these guys. So let's talk a little bit about solubility of amines. Primary and secondary. Primary and secondary amines have the ability to hydrogen bond. So if you remember, ammonia is something that can hydrogen bond, which is basically what these guys are derivatives of. And that is because amines like ammonia have a bond between hydrogen and nitrogen, which is a nice polar type of group, positive, negative. And in this particular case, it can form hydrogen bonding, which means when water comes around, it's able to bond and make hydrogen bonding happening there. So that makes it really soluble in water. A lot of them are soluble in water. Tertiary amines, though, cannot hydrogen bond with water because it has no hydrogen attached to the nitrogen, because it's replaced with all those carbon groups like we saw in the previous sort of example. So because tertiary amines don't have that ability to hydrogen bond with water, it's going to obviously affect its solubility with water. So it won't be able to really be soluble in water. But primary and secondary guys have those hydrogens that allows them to interact well with water. Again, like much other things, as long as there's not super big carbon groups attached to that nitrogen, it kind of gets in the way. You're going to have pretty good solubility, like most of those guys that can hydrogen bond. So primary amines can form more hydrogen bonds than secondary amines, and that's because it has 2 hydrogens, a primary amine. A secondary amine only has 1 hydrogen, and as we just talked about, tertiary amine has no hydrogen, so obviously it cannot form any hydrogen bonds there. So like alcohols, smaller amines, including tertiary ones, are soluble in water as they form hydrogen bonds. They can sort of hydrogen bond with water. Maybe I misspoke there in terms of our tertiary guy, but it's not supplying the hydrogen. It is the water that would be able to kind of do that move with it. So it can still interact with water, not as well as obviously a primary or secondary one could. So if amines have more than 6 carbons, the effect of that hydrogen bonding drops down. So kind of the general rule in organic is as you reach like kind of that 4, 5, 6-ish range of carbons, you start to see a lot of decrease in solubility, even with groups that have the ability to do so. Again, things just sort of get in the way. You could kind of see, you know, these big groups here, right? And it's like nitrogen, water's got to try to get in between all those guys, and it's not going to work really well with water, which is a relatively small one. All right, which of the following compounds are soluble in water is the first one. Should be, it's a primary amine, so it should have no problem. Second one here is a secondary amine, which also it should have no problem. Is it soluble in water? There's no amine there. That's an alkane. It's all non-polar, which again is going to try to use the dispersion forces. Water using hydrogen bonding, not going to mix really well. They're going to really separate out into different layers. Yeah. So the first two should be good. The last one, not so good in terms of that. Now, amines, because they're really based off of ammonia, which is a weak base, surprisingly enough, can basically act as a base in the sort of the Bronsted-Lowry definition. So in this particular case, just like ammonia can act as a base, which means it would accept the H+ from water. Same deal is going to happen here. It's going to accept the H+, and that's why it gains an extra hydrogen on this side and has a plus. When it does so, it produces hydroxide, which is why this is basic. And these guys are bases because it's able to produce hydroxide in solution. So remember that a lot of weak bases are these sort of amines. They don't have hydroxide sort of on them, like say sodium hydroxide or potassium hydroxide, but they are able to, when they're in solution, react with water and produce hydroxide, which makes them again bases. Also, why we see these reversible arrows, because these are weak bases, which are weak electrolytes, which means it's a reversible type reaction that we talked about a number of times throughout the semester, I think. Now, neutralization from amine salts. An amine salt forms when amines are sort of in that reaction that we just saw there, that sort of Bronsted-Lowry neutralization reaction. Some of these are responsible for some odors of fishes, and you can kind of neutralize it by adding some acid, by squeeze a little lemon on your fish and all that good stuff. So here, if we take an amine, once again, it's going to act as a base, going to send the H+ over. This is going to make our amine salt. And we're not going to obviously name the salts, but you get a salt, kind of similar to a basic acid-base reaction where you make salt and water. In this case, you're just kind of making the salt in this case, not really water. And same thing here, H+ going to come on over. And again, we're going to gain a hydrogen and a plus. And this is why it's referred to as a salt, because it has that ion there to balance it out. So some properties of ammonium salts. Amines are usually converted to their salts before they're used in some type of drug. Solids at room temperature. Here are some things like ephedrine and hydramine as well, which is like Benadryl. You can see our amine salts here, which is basically over here. Cocaine as well, and so we also I know, it sounded great. I know. So we have our amines over here as a process of that from cocoa leaves. So cocaine, hydrochloride, and ammonium salts can be converted back to its amine in a sort of free form there as well. All right. Good thing. Alkaloids, these are physically active compounds produced by plants that have nitrogen. So this is like nicotine over here. Again, you can see our amine group there. Also, whoops, over here as well. Where we go? Caffeine, or good amine, I suppose, if you like coffee and all that good stuff there. There are amine groups as well. Morphine, also an amine over here. All right, so why don't you draw these guys? All right, so again, we're going to draw an amine. So we'll start with our nitrogen here. And methyl means 1 carbon. And we'll put the hydrogens. And propyl is 3 carbons here. We'll put our appropriate hydrogens. This basically makes it a secondary amine, which means it should again have 1 hydrogen left over as well. Yeah. Any questions on that one there? Yeah. It doesn't, like if you turned it, it's all good. Also, if you put the hydrogen on the bottom, it's all good too. Yeah. It doesn't really matter. Yeah. But you do need the hydrogen, obviously, because it's a secondary, so it should still have that 1 hydrogen. Other questions on that one? So aniline here is really our benzene ring that has a nitrogen. And in this case, that's going to be carbon number 1, which means that carbon number 2, I should have a chlorine. And in this case, we still need to kind of complete out our nitrogen. This is basically going to be a primary amine, which means it actually needs 2 hydrogens in this case. Yeah. Any questions on that one there? And again, obviously you could put the NH2 group on any of the carbons, and then just as long as you went 1 carbon over for the chlorine, it's all good. It's just the same thing turned. Any questions on amines here? It gets 2 hydrogens because basically nitrogen needs kind of like 4 electron pairs, basically. So it has 1 from the bond to the carbon, although we don't draw it a lot. Amines have a lone pair sitting there, so that's 2. So to get it really to 4, you make it up with the hydrogens, kind of similar to what you do with carbons. Other questions? Okay. All right, the last one of it all here, and this is going to be an amide, which is a carbon-oxygen double bond to our amine. So it basically is, as you might be able to imagine, it is a carboxylic acid and an amine that comes together, basically, is how you get to this guy. So here's an amide, which is in Tylenol, for example. And there is our amide bond. This is also a peptide bond that happens with proteins, basically, is this bond right here when they come together. So amides basically replace the OH group on a carboxylic acid with an amine, basically, or ammonia. And again, that's basically how you make it. You take carboxylic acid and an amine and basically put them together. You actually take out water, just like kind of everything else there. So if you took a carboxylic acid and you took an amine, you basically just take out water and you squish them together. And now you have your amide sort of connection. So it's basically kind of similar to how you make this esterification reaction. Take out water, squish them together, and you get your amide. Which is pretty much what I just showed you there. There we go. So to prepare an amide, like I said, take out water and put the amine and the carboxylic acid together, and you will have your amide. It always has this connection point, which is sort of also how you know if you had to break it apart, that is exactly where it should break apart. So kind of like the ester where you have the carbon, oxygen, oxygen, and you break it there. With the amide, you have the carbon, oxygen, nitrogen connection. And again, that is basically where it would be a break apart if you needed to. All right, so if we were going to do this guy here, we would look at it, and we're basically going to take out water which is going to be this guy and really one of those H's. Now we're just going to connect that guy in. And again, nothing here changes except I drew the double bond in the wrong location. That would be bad. Let's try that again. All right. So if we put the double bond perhaps in the right location, that would be good. So the connection though is again that connection where the nitrogen gets connected to the carbon. We have one hydrogen still left. And again, everything else stays the same. So again, this is really the amine part. All right, and this is the carboxylic acid part. And again, really the only thing that came out there was water is pretty much what we took apart. Any questions on that one there? So a carboxylic acid and an amine will give you an amide. Very similar, almost identical to what you do with the esters. Take out the water and just put everybody in there. If you remember sort of the connection, that will help you sort of align things where they need to go. All right, so hydrolysis of amides, maybe I care. All right, let's take a look and see. So clear, if I didn't care about it, you shouldn't care either, I suppose, right? So that would be a good thing. All right. So you do not have to worry about naming amides or anything like that. But let's talk about what happens in terms of the hydrolysis reaction, and let's just do a fairly simple amide here. So we have pretty much the same sort of situation as we had with the esters in the hydrolysis. We have an acid hydrolysis where we're going to add some water. And in the acid hydrolysis here, we're going to break it apart right there. We're going to add some water and a little HCl as the acid. And when we break it apart, we will get back our carboxylic acid. So once again, we will build back our carboxylic acid in this particular case. And in this case, we will get a couple of hydrogens coming in to our amine. And we will basically build back something like this, ammonium chloride here. In this case, we actually are going to steal a hydrogen from the acid and also the water here to build back our carboxylic acid and ammonium salt. In a base hydrolysis, you actually will get a carboxylic acid salt and an amine or ammonia will basically come back. So if we did this with a base, again, we'll use the same guy maybe. That's small. Or use the guy that's on the bottom there. So they use sodium hydroxide, which is a strong base. Once again, it's going to break apart here. And in this case, we will get kind of like our carboxylic acid that we had before, but we're going to get the salt part. So we're not going to get it completely back. So we'll get that salt like we had with the ester. They're pretty much identical reactions. You'll have the sodium in this case because it's sodium hydroxide. And if we just kind of cross off everything we use, there's still a hydrogen left. And that hydrogen is going to come over here to the amine part and sort of build that guy back as well. So we'll get this here. And again, that hydrogen is the one I circled, comes back from the sodium hydroxide. So very similar to the ester acid hydrolysis, though, we actually will get the carboxylic acid and we'll get some type of ammonium salt, which is basically like NH4 plus, something of that nature. In the base hydrolysis, again, we'll get basically the amine back, but we'll get a salt of the carboxylic acid. So slightly different on each of those. Any questions on that there? All right, so once again here, this is the base hydrolysis breaking apart. And again, in the base hydrolysis, we get the salt and we get our amine back by putting the hydrogen back together over here. All right, some bread, some pasta, all the good dinner stuff, I suppose. All right. And it says hello to you. So we're going to first talk about chiral molecules, and we'll talk about why the hands are there in just a second. But chiral molecules have the same number of atoms, but they're arranged differently in space. They have one or more what is referred to as a chirocarbon. And basically, for something to be a chirocarbon, you need actually 4 different groups attached to the carbon. So if something has 4 different groups attached to it, say you have a carbon, and I'll just use the alphabet here. And we'll use D in this case, E. So if we have 4 different sort of groups attached to that carbon, that is what is referred to as a chiral carbon, and that would be a chiral compound. They are mirror images that are non-superimposable. So what that means, hence the hands, if you put your hand up to the mirror, you get your other hand, yes? And if you take the image out of the mirror, you could twist it around as much as you like. You'll never get them to fit perfectly on each other. Thumbs on the wrong side, still thumbs on the wrong side, yes? Thumbs on the right side, but one's palm up, one's palm down, not the same, yeah? So they'll never, don't hurt yourself, yes? But if you try to move around with your hands, you'll never be able to superimpose your left hand on your right hand, and everything will be in the same orientation, you know, palm up, palm down, and that type of thing. So an achiral molecule, as we'll talk about, so that's a chiral molecule where we have non-superimposable mirror images. An achiral molecule, you basically do not have 4 different groups. You have at least 2 guys that are the same, and those have mirror images that you can superimpose. So if you have something that has basically not 4 different groups attached to it, that is more of an achiral where you can take that mirror image and superimpose it. So in this case, if we took the mirror image of this first molecule here, we would get this molecule. And if we took this molecule out, although it may be hard to sort of visualize, and we rotated it, there's always going to be something in the wrong location. So maybe we might get some things to match up okay, but you'll always have sort of an element in the wrong location. And that's what makes it basically a chiral molecule. So in this case, as you can see, the bromine is in the wrong location from the original guy, and vice versa over here. Although these guys match up okay, you cannot get all 4 of those groups to match up perfectly when you have a chiral molecule. Achiral, as I mentioned before, is when you do take the mirror image and you basically have not 4 different groups. So in this case, we have 2 bromines that are identical to each other. So in this case, when we do take the mirror image, we can very easily just kind of rotate the molecule. And when we rotate the molecule, we can get the mirror image to fit perfectly over the original image. And that's basically because it's got 2 points of symmetry. Basically, it's got 2 things that are the same. So it allows it to be able to actually fit perfectly on top of one another, which does not happen, obviously, in a chiral molecule. So chiral molecule mirror images are non-superimposable. Achiral molecules, the mirror images are superimposable with some rotation. You could get it to fit perfectly on top of each other. Any questions on that there? So here are some everyday chiral and achiral sort of things. We have gloves, which are chiral, golf clubs. We have a soccer ball. Right-handed scissors, I suppose, is chiral. I don't know. I don't know. There's right-handed scissors, left-handed scissors. Okay, let's take a look at the first one here. So we'll go with this carbon, and that looks different than that, which looks different than that, which looks different than that, which means this should be a chiral molecule. Looking at this carbon here, that is different than that, which is different than that, but that is the same as that, which means that is not 4 different groups. So that's going to be achiral, right? And lastly here, different, 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 and different, which means it is chiral. Any questions on that there? Which one of these mirror images can you superimpose? Okay. It would be B, right? A and C, the mirror image will not superimpose because they are chiral. Yeah. Okay. There it is. Now, Fisher projection is a 2-dimensional representation of 3-dimensional molecules. We usually place the most oxidized group towards the top. We use vertical lines in place of dashes for bonds that go to the back of sort of the paper. And we use horizontal lines in place of wedges, or sometimes when people use wedges, that means it's sort of coming forward or out of the paper. Kind of the dashed little line means it's kind of going back of the paper. So you sometimes will see these things drawn like this, which means it's sort of going back of the paper. And some people will still use wedges, which means it's sort of coming forward out of the paper in that case, if you were to draw something like that. And that's what we kind of see here. This is a very common sort of representation of carbohydrates, where a lot of times we actually just kind of use almost like line structure, if you will. So usually you'll have some type of organic group there at the top of your carbohydrate, and kind of like line structure everywhere, they kind of intersect. These are all carbons, basically. So everywhere that intersects, those are all pretty much carbons. So this particular one has 1, 2, 3, 4, and 5 carbons. And then obviously at the ends here, there'll be some OHs, some H's, you know, sort of happening. Maybe in this particular case. So that's a very common way, kind of like almost line structure, just kind of use lines, and intersection of those lines is where we find carbons in carbohydrates. So this is glyceraldehyde, and on both of those, and one is L and one is D. And what L and D, as we will see, basically represents is L for left, if you will, D for right. And what we're talking about is the last OH group at the last chiral carbon, away from the sort of organic group, if you will, that's on top. So in this particular case, there's our organic sort of group. This right here is the last chiral carbon, and the OH group is on the left-hand side, so that is L. This is our last chiral carbon away from the organic group. The OH group is on the right, so that is D in this case. And that's basically what L and D represents. I will say probably 9 times out of 10, you could usually find the last chiral carbon above this guy. Yeah, so if you see that CH2OH, it's usually not 100% of the time, but a lot of times it is that last carbon right before it is oftentimes your last chiral carbon. And that's usually the one that you would look at to determine sort of L or D in terms of the carbohydrate as to which side that OH group is on. Any questions on that there? As I just mentioned, our D and our L, depending on which side. And again, a reminder that those intersection points, they are carbons here, yeah. All right. All right, so let's finish up with this one. Indicate whether each pair is a mirror image that cannot be superimposed. Almost a double negative, I think, that question, I think. Okay, so to help us decide, we should probably decide, are these chiral carbons or not here? So that is a group that's different than that one, that's different than that one, that is different than that one. So that obviously is this mirror image. So if you put a mirror there, perhaps that's what you get staring back at you. So this is chiral, which means this mirror image is non-superimposable. But to really confuse people to answer the question, then that is yes, it cannot be superimposed. This is the answer to the question. So this is a non-superimposable image. Here, again, we look at it and we do see 2 groups there that are not different, which means this is achiral. And that means that we can superimpose. So yes, it can be superimposed, which for the answers to the question would be no, because it cannot be superimposed, because it can be superimposed. So it's a kind of weirdly worded question, I think. Yeah. Any questions on that there? All right, we will lay it up there for now.